in this question may appear to be difficult, but it is a very easy one if you know the concept of combination of springs in the case of SHM. Here we have 4 springs of spring constant K1, K2, K3, K4, where they are arranged as shown. This is a mass M, and there is a constant force F acting on this block of mass M. We need to find out the amplitude and frequency of the resulting SHM. Now, there is no doubt in our mind that this motion is SHM because it is a combination of spring and mass. Now, here's a trick. Whenever there are springs in series, we apply the formula for combination of resistances in parallel. This is K1, this is K2. Therefore, the resultant spring constant can be assumed to be K1 K2 upon K1 plus K2. This is found by, let this be K. 1 upon K is equal to 1 upon K1 plus 1 upon K2. Therefore, K is equal to K1 K2 upon K1 plus K2. Similarly, for this pair again, we replace it similarly. Therefore, the final system becomes block of mass M, force F, 2 springs. The spring constant of this be, let this be K and let this be K dash. K is equal to K1 K2 upon K1 plus K2. K dash is equal to K3 K4 upon K3 plus K4. These are the resultant spring constants which can be replaced here. Now, whenever the springs are in parallel, we apply the formula for combination of resistances in series. So again, the resultant spring constant, that is the resultant spring, one single spring which can replace these 2 springs, is equal to of spring constant K plus K dash. So this whole system can be converted to a single spring and a mass with a constant force F acting, where K double dash is equal to K1 K2 upon K1 plus K2 plus K3 K4 upon K3 plus K4. So this is the resultant spring constant of a single spring which can replace all this chaos over here. So let us write this in one corner. K double dash is equal to K1 K2 upon K1 plus K2 plus K3 K4 upon K3 plus K4. Now, for finding out the amplitude and frequency, let us first see that initially the spring was at its natural length and the block started with velocity is equal to 0. Therefore, this is definitely the extreme position of the SHM of the particle. Now we need to find out the amplitude. For that, let us find the equilibrium position, and we know that the distance between the equilibrium position and the extreme position is equal to the amplitude. Therefore, at the equilibrium position, K double dash into X, that is, this will be displaced by some amount X such that the net resultant force becomes 0. Therefore, K double dash becomes equal to F. Therefore, X becomes equal to F upon K double dash. So we get the answer for the amplitude of the SHM to be F upon K double dash, which is equal to F upon this quantity. Now we need to find out the frequency of SHM. For finding out the frequency of SHM, we know the equilibrium position. We displace the object from the equilibrium position by a distance x and find out the restoring force. At the equilibrium position, F was equal to K double dash x naught. Let x naught be the original extension in the spring from here, and x naught, as we knew, was equal to F upon K double dash. Now this was the equilibrium position with in which the extension in the spring already was x naught. We displace this object from the equilibrium position by a displacement x. Now the net restoring force we need to find out. We always displace the object from the equilibrium position by distance x, and then we find out the restoring force. The restoring force is the net force bringing the object back towards the equilibrium position. That is equal to k into k double dash into x naught plus x minus f. So this becomes equal to k double dash x naught minus f plus k double dash x. Now k double dash x naught minus f is equal to 0. Therefore, the net restoring force becomes equal to k double dash x, which is directly proportional to x. Therefore, the frequency of SHM can be written to be time period is equal to 2 pi root over m upon k double dash. Frequency is equal to 1 upon t is equal to 1 upon 2 pi root over k double dash upon m, where the value of k double dash is substituted to be this. So an important thing which we learned here is that a constant force can never change the time period of a SHM. So even when the spring block system is doing SHM in the vertical direction, there is a constant force of gravity acting on the block, but since it is a constant force, it can never change the time period of the SHM, and the time period of the SHM still comes out to be 2 pi root over m upon k, as it did in this case. So in the case of constant forces acting on the block, always neglect that to find out the time period of the SHM directly to be 2 pi root over m upon k double dash in this case, where k double dash was equal to this.